Hello students, welcome you all. So today I will explain the structural elucidation of this progesterone steroid. Now this progesterone, it was isolated by Butenant and co-workers. So Butenant and co-workers were the scientists. Butenant and co-workers. They isolated the progesterone in 1934 from this corpus luteum. Corpus luteum of pregnant sows, and also it was also isolated from adrenal cortex and placenta. So these all are the female organ, and this progesterone one of the female hormone. So this progesterone female hormone, it was isolated from these female organs. The structure of this progesterone, if we see the structure of this progesterone, then it is like this. So no doubt it will have a steroidal ring. So this is the steroidal ring. Okay, this is the steroidal ring, and it contains the 17. Okay, it contains the 17 carbon atom. If you see 10, 11, 12, 13, 14, 15, 16, 17. So 17 carbon atoms, which corresponds to gonane nucleus. And then if I add one of the angular carbon atom here, angular methyl group here, then it is 18th one. Then it will become this 18th, it will become the estrane nucleus. Now if we add another angular methyl group, then it has the 19 carbon atom. Then it will become the steroidal nucleus is the androstrane. Okay. And if I add two more carbon atom at 17th position, this is the 17th position. So suppose I add two more carbon atom here, then it will become the pregnane nucleus. Now this is progesterone. So this is progesterone. So here at 17th carbon atom we have COCH3 group. Okay, this is COCH3 group. And at this third carbon atom we have another keto group. So one of the keto group is present over here, another keto group is present at this position, and one of the double bond is present at this position. Okay, so if I number it, then it is 1, 2, 3. So 4, 5, 6, 7. This is 8th carbon and 9th carbon. This is 10th one. 11, 12, okay, this is 13, this is 14, 15, 16, 17, 18, 17, then this angular methyl group 18, this is 19, this is 20, and this is 21. So overall if you will see, it has 21 carbon atoms. So it corresponds to this pregnane nucleus having the 21 carbon atom, and this progesterone it has the pregnane nucleus, and as it has this keto group, two keto groups are present. One of the keto group is present at this third position, whereas the another keto group is present at the 17th position, that is in the form of this side chain. Another keto group is present, and one of the double bond is present at 4 and 5 carbon atom. One of the double bond is present. Okay, so if we want to prove the structure, if we want to prove the structure of progesterone, then what should we have to prove? So we should prove that one of the things, that is the common thing, that it contains the steroidal nucleus, which we have proved earlier also. If we distill it in presence of selenium, then it will give the deals hydrocarbon, one of the thing. Second, we have to prove two keto groups are present. So two keto groups can be disproved if we treat it with the either DNP, or if we treat it with hydroxylamine, then it will give the oxime. Okay, as it contains the two keto group, then it should give the dioxime. It should give the dioxime. One of the double bond is present over here. It means it will undergo reduction. Catalytic reduction may takes place. So, and it may absorb the one molecule of hydrogen. But if it undergo catalytic reduction, then this keto group can also be converted into the hydroxyl group or secondary hydroxyl group. Okay, so how can we prove the structures? So let's come to the structure elucidation. So its molecular formula, if you will see the molecular formula, then as I told, it contains the 21 carbon atom, pregnant nucleus. Then number of hydrogen, if we count the number of hydrogen, then it will have the 30 hydrogen atom is present, and 2 oxygen atoms are present here. So 2 oxygen atoms. Now if we see the double bond equivalent, then double bond equivalent if we count, then using the formula, number of carbon atom plus number of monovalent atom, minus number of monovalent atom divided by 2. Okay, no trivalent atoms are there, no nitrogen is present over here, so we need no need to add the number of nitrogen atom divided by 2 like this. So now plus 1, we may add plus 1. So how many? So 22 minus 15, this 22 minus 15, it comes out to be 7. It comes out to be 7. It means 7 here, if you will see the 7, this corresponds to 1, 2, 3, 4 cyclic rings, and 5 is this double bond, 6 double bond this one, and 7th double bond of this keto. So 2 keto groups means 2 double bond, and 1 this carbon-carbon double bond, 3, and we have the 4 cyclic ring. So that's why its total it corresponds to 7. It means we have calculated the double bond correctly. Now, after this, if this progesterone, that is, if progesterone C12H30O2, when it was treated with suppose hydroxylamine, then it forms the dioxime. It forms dioxime. So what does it indicate? Formation of this dioxime, it indicates that it contains therefore 2 keto groups or 2 carbonyl groups are present. 2 carbonyl groups are present. Okay. Now, when this progesterone it was treated with hydrogen or catalytic hydrogenation was done. So catalytic hydrogenation, then it was seen that it absorbs 3 molecules of hydrogen. So if 3 molecules of hydrogens are absorbed, then it means, and also the formation of dihydroxy compound was seen. So it absorbs, that is, it absorbs 3 molecules of hydrogen and dihydroxy compound was formed. Dihydroxy compound forms. So formation of this dihydroxy compound, indicate that this 2-carbonyl group, it should be the keto group, because the keto group on hydrogenation, on reduction, it gives the 2 secondary OH group. So it means therefore this it has 2 keto group and 1 carbon-carbon CC bond. Okay, so now next, so we have proved 2 things, that is, it contains 2 keto group and 1 carbon-carbon double bond. Now, if progesterone it was treated with selenium distillation, then it was seen that it gives the Diels hydrocarbon. So the formation of this Diels hydrocarbon, what does it indicate? It indicates that the progesterone contains the steroidal nucleus, that is, it contains 1, 2, 3, 4 rings. That is, therefore, it contains steroidal nucleus. That is 4. That is, it is tetracyclic. Okay. Now, so this tetracyclic nature can also be proved if we completely saturate this molecular formula. So if we have, suppose C12H30O2, if we do the saturation, if we convert it into the parent hydrocarbon, or if we completely saturate it, it means it is absorbing 3 hydrogen atoms. So after absorbing 3 hydrogen atoms, we may get the saturated hydrocarbon. So this will become C12H36. So this is the saturated hydrocarbon. This will becomes the saturated hydrocarbon, and this corresponds to the general formula CnH. Okay, this corresponds to sorry. So it should be not C21. It should be not 12. It should be C21. It should be C21. Okay. So C21 means it will be 36 minus 22. Okay. So what does it tells? So 36 CnH2n minus 6. Okay. So means 42. So 42 minus 36, it is 42 minus 6, that is 36. Means it corresponds to the tetracyclic. It also corresponds to tetracyclic. Okay, means progesterone is tetracyclic in nature, or otherwise if we calculate the double bond equivalent of this saturated molecular formula, completely saturated molecular formula, then if we calculate the double bond equivalent, then it comes out to be 21 minus 36 divided by 2 plus 1. So it comes out to be 22 minus 18, it comes out to be 4. So this 4 corresponds to the 4 rings. Again this 4 corresponds to the 4 ring. So like this. So this is one of the things. Now as you can see, that one of the keto group is present and another this double bond is present. So this is alpha beta unsaturated carbonyl compound. So we can say that this progesterone is a alpha beta unsaturated carbonyl compound. So this was proved by the UV spectra. So when the UV spectra was taken, so UV spectra gives lambda max at 240 nanometer. So UV spectra gives lambda max at 240 nanometer. So this indicates, therefore, it is alpha beta unsaturated carbonyl compound. So how can we say? So we can also find the lambda max. We can also calculate this lambda max by using the Woodward-Fisher rule. So by Woodward-Fisher rule, the base value for this alpha beta unsaturated carbonyl compound, so this is 215 nanometer. So base value, this is a 215 nanometer. And if we have, you can see one of the this alkyl or ring residue is present. So this is one of the ring residue. So this is one of the ring residue. This is another ring residue. So two ring residue at beta position. So as it is alpha position and this is beta position. This is alpha beta. So two ring residues are present at the beta position. So it corresponds to 12 nanometers. So for one ring residue, the increment is by 12 nanometer, and as two ring residues are there, that's why the increment will be by how much? By 24. So increment by 24. So total it comes out to be 239 nanometer, which is very close to this observed value. So calculated value is also very close to the observed value. So that's why we can say that this progesterone is an alpha beta unsaturated carbonyl compound. Okay, now if we next thing that which can be proved, that the position of this keto group, one of the keto group is present at the 17th position, as you can see. Another keto group is present at 3rd position, and the double bond is present at the 4th and 5th carbon atom. So now we should prove the position of these two keto group as well as the position of the double bond. So how it was proved? So when this progesterone, when it was undergone when iodoform reaction, so let's see the next point. If you want to prove, then when this progesterone, that is C21 H30 and O2, when it was progesterone was treated with NaOH plus Br2, that is bromoform, or we can say iodoform reaction, suppose I2. So when iodoform reaction was performed, and what was seen, that it was giving one molecule of iodoform. So one molecule of iodoform was formed. So this one molecule of iodoform, what does it indicate? So therefore it contains this COCH3 group. It contains COCH3 group. Means if we do the iodoform reaction for this, then this CH3, that would be, means it will be break from here, and that would be converted into CHI3, whereas this would be converted into the acid part. So this would be the acid part and this would be the iodoform part. If two molecule of this is two COCH3 group would be present, in that case we should have the two molecule of iodoform that will be formed. But here only one molecule of iodoform was obtained. It means it contains the one COCH3 group. So, and this COCH3 group, it must be present because this progesterone contains the 21 carbon atom, and out of this 21 carbon atom, the steroidal nucleus contains the 17 carbon atom, and 18th one is present at this one at 13th carbon atom, 19th, and this 18 and 19th are the two angular methyl group. So 17, 18, 19, and we know that in by the nomenclature of this steroid, we know that the next two carbon atom that should be present at the 17th position. So therefore these two carbon atom must be present at the 17th position as a side chain. Therefore we can write the COCH3 group is a side chain present at C17 position. Okay, that is this position. Okay, so this position is this is side chain. So this side chain is present. Okay, now next thing, when another thing that was seen, this progesterone, it was finally this progesterone was synthesized from cholesterol also. So, and in cholesterol we know that one of the OH group is present at 3rd position, and the double bond is present at 5th and 6th position in cholesterol. Okay, so as it could be synthesized from the cholesterol, so that's why, and it was also proved by the X-ray that this progesterone contains the steroidal nucleus, and finally it was synthesized from cholesterol. So this confirms that the progesterone should also contain this another keto group at the 3rd position, and as it is a alpha beta unsaturated carbonyl group, that's why the double bond should be present at 4th and 5th position, not 5 and 6th position as like that of the cholesterol. So what we can write as by X-ray, it was confirmed that progesterone contains the steroidal nucleus. And it was also synthesized from stigmasterol as well as the cholesterol. So what does it indicate? So this indicates that another keto group, one of the keto group is present at the 17th position. So therefore next keto group must be present at C3 position, and the double bond should be present at the 4th, 5th position, which is confirmed by the UV spectra, and the CC bond must be present at this 4 and C4 and C5 position, as confirmed by UV spectra, Okay, so on the basis of these experiment, the structure of the progesterone that was given like this. So steroidal nucleus at 13th and 10th, at 10th and 13th position, one of the angular methyl group, two angular methyl groups, this one. At 17th position, COCH3 group. At 3rd position, another keto group. And at 4th and 5th position, double bond by the UV spectra, because UV spectra by UV spectra it was confirmed that this progesterone is a alpha beta unsaturated carbonate compound. Okay, so this is about the structure of the progesterone. Now let's come to its synthesis. So now, so synthesis, it was given by butenant. So synthesis by butenant in 1939. In 1939, its synthesis was given. Now, so it was synthesized from cholesterol. As I told you, it was synthesized from cholesterol. So what was the strategy that was followed? So strategy for the synthesis. So one of the strategy that we know that the cholesterol contains one of the side chain at this 17th position. So if you see the cholesterol is, this is the cholesterol structure. This is our cholesterol. Okay, so this is the cholesterol structure. Okay, this is the cholesterol structure, and from this cholesterol we have to synthesize this progesterone. So how can we synthesize? One of the thing that we should remove, first strategy to remove the side chain. So how can we remove the side chain? We have also discussed it in the synthesis of this testosterone. So how can we remove the side chain? The side chain can be removed by the oxidation. So if we treat it with the chromium oxide, then this side chain that would be converted into this one, and it will be converted into cyclohexyl methyl isocyclohexyl methyl ketone. So that would be converted. So here it would be broken from here, and so this would be converted into the keto group, and we can write it in this form. So now this keto group that should be converted into this COCH3 group. So how we can convert it? So we will convert it by treating it with HCN. So if we treat it with HCN, then that would be converted into use OH and CN. So this HCN, so that would be converted, and that would be, so it would be converted into this one. Now finally in presence of the dehydration, so in presence of PuCl3 and pyridine, so dehydration of that will occur. So dehydration that will give you the CN, and then treating it with CH3MgBr or Grignard reagent, so we can convert it into your COCH3 group, and one of the double bond is present here, and this double bond can be reduced. By the H2 nickel or Raney nickel, and that will be converted into your COCH3 finally. So this is one of the strategy that was followed. And second strategy, to convert this OH, secondary OH, that should be converted into the keto, and the position of double bond should be shifted from this 5-6 to the 4th-5th position. And second strategy, to convert the secondary OH into keto group and shifting of carbon-carbon bond from this 5-6 to your 4-5 position to 4-5 position. So these are the two strategies, and this can be done easily by using open-air oxidation. So if we do the open-air oxidation for this open-air oxidation in presence of aluminum tertiary butoxide, okay, then what we can find, we can convert this one here into the keto, and the double bond that would be shifted to this position, and we can write like this. So these two strategies that should be followed here to convert this progesterone, to convert this cholesterol into this one. So let's see the synthesis. So if we see this synthesis from cholesterol, so this is our cholesterol. And first of all, now before removing this chain by the oxidation, so what we should do, we should first protect this OH group as well as this double bond. Okay, so let's protect this one by the acetylation, and second by using this bromine. We may add the bromine over this double bond. So why this has been done? So otherwise, so this would be converted into this OAC, and here we have one of this anti-addition of this bromine that will takes place. So this bromine anti-addition, and we have here okay. So now we may do the oxidation. Well, now in presence of chromium oxide, we may do the oxidation. So after this one, what we may get the okay. So otherwise, if we don't protect it, if we don't do this step, otherwise what will happen? So this double bond here, in presence of chromium oxide, it may break from here to convert into keto, and this may get also be converted into this keto. So that's why we have done the protection first. Now we can deprotect it. So it may be deprotected in presence of this zinc acetic acid. In presence of this zinc acetic acid, now we may deprotect it. So the removal of this ZnBr2, and here that would be converted into OH, and okay, so we have double bond over here, and okay. Now in next step what we should do, again we should protect this one only. Now I will protect only this OH group. So why we have done it, so I will tell you. So now again it should be protected. So after this protection, we will have the OAC again. So because we have to treat it with the Grignard reagent. So Grignard reagent that may do the acid-base reaction from this acidic OH. So that's why, so further we have to treat it, this keto group, that is further we should treat it with the Grignard reagent. First we will convert it into the CN, then we will treat it with the Grignard reagent. That's why to prevent the reaction of this OH group with the Grignard reagent, that should be protected. So again we will protect it, and we may convert it into this one, and so now what we may do, so treat it with the, we may treat it with this HCN, and so nucleophilic addition over this carbonyl that will takes place, and OH and one of the CN. Okay, so this nucleophilic addition of this one will occur, and finally it was treated with this PuCl3 in presence of pyridine. So this will attack over this one, and finally, or we may write it in this way also. And finally the Cl will remove pyridine and will remove this one of the H here. So we will get the, and this here one of the hydrogen is present over here, pyridine will remove this one hydrogen also, and finally what we will see, so this will get removed. Okay, this will get removed like this. So the removal of H2O that will occur in presence of PuCl3, removal of H2O. So removal of this H2O. OAC, and so here we have the CN group and one of the double bond over here like this. So if you want to see the mechanism for this, I am writing the mechanism. Suppose if we have this OH group, and this CN over here, so this will get reacted with the, this will give the lone pair to the vacant d orbital of the phosphorus, and this will go over here, and now this pyridine which is present, over here, so this will take this H plus, and finally what we may see, so one of the Cl that will be removed, minus, and what we may see that here Cn, and here this oxygen is forming a bond with phosphorus, and this is this one Cl and Cl, one of the hydrogen is present again over here. Now pyridine will again, it will take this one and like this. Okay, so in this way you may see that double bond, and this will get over. Okay, plus we have a pyridinium ion like this. Okay, so this is the mechanism for this one. Okay, so now so finally it will give this one, and this one in presence of this Grignard reagent CH3MgBr. So if you see the reaction of this Grignard reagent, so if we have a CN over here, then it will react with this, we may write triple bond over here, CH3MgBr, and this is plus, this is minus, and what we may write, this C double bond N minus MgBr, okay, and one of the CH3 is present over here. So finally after hydrolysis, so we will get this COCH3 and plus this NH3 and plus this Mg, Pr and OH. Okay, so after hydrolysis, this we will get. So finally this is the mechanism for this one. Now, so there we can write here. We may write here this product. We may write the product OAC and COCH3, and one of the double bond is present. Okay. Now in next step, that would be the partial reduction in presence of this H2 Raney nickel. So this will reduce, partial reduction will occur over here. This will have the COCH3, and in next step, what we may do the open air oxidation, and we may deprotect this one. So we may, after this deprotection by the hydrolysis, we may deprotect it. So I am writing over here. So this will be deprotected, and then in open air oxidation. So in open air oxidation, in presence of ammonium tertiary butaxide and cyclohexanol, so what it will do, that it will be converted into the keto, and this double bond will shift at this position, and we will get the progesterone. So we are getting the progesterone. So we may write the structure. So this is our progesterone. So this is the synthesis of progesterone. Hope you are understood. Thank you.